Thank you very much. Also, thank you for the possibility to present here. I unfortunately wasn't really aware of the format, that this is a seminar series kind of thing, so I came only for 1 week, but I hope if something comes up, we still can discuss after the talk. So I'm Csanad from the Eötvös University, Budapest, and I will indeed talk about Lévy-walk. I show here a Lévy type of beer. This is, I guess, more home of wines, but in a bring your own bottle sense, I just show it. And if you are more interested, then we organize a workshop in December in Budapest, the Zimányi School, also about hydrodynamics. So there, maybe you can taste this as well. But it's not only a bring your own bottle, but also a bring your own equation type of talk, because I will present lots of thoughts with far fewer equations than before, and more plots, and I hope that we will be able to make some sense out of it. Right. Oops. So, first of all, what is Lévy-walk? I guess many heard of the concept. Is a very, very general cross-science concept. It starts from basically the central limit theorem. If you have random variables which have no finite second moment or even a first moment, then the central limit theorem does not apply. And then the limiting distribution of that the sum of those random variables follows is not a Gaussian, but a Lévy stable distribution. And this is given by the generalized or proven by the central limit, generalized central limit theorem. And this behavior is found in many, many systems, from foraging of animals, swarm dynamics, and various microbiological, chemical, and physical processes. The main point always is that that while in normal diffusion or normal random walk, you do small steps, and then the step size distribution has a finite second moment or a Gaussian tail. But in anomalous diffusion or Lévy-walk or Lévy-flight, you do sometimes very large steps, and these the non-zero probability or strong probability of these large steps creates a heavy tail in the step size distribution. And it appears that it applies in high energy physics as well, but for that we need to start a little bit earlier from femtoscopy. I guess also everyone knows the concept. Just let me very briefly introduce it. Hanbury, Brown, and Twiss were radio astronomers, or Twiss was actually a mathematician, and they observed stars with radio and optical telescopes. And their discovery that was not understood at the time was that intensity correlations appear if they correlate two detectors and then increase their distance or decrease their distance, then in the multiplied signal, something beyond the statistical probability appears, and that we can call correlation. And then this correlation signal actually reveals the size of the star, which is otherwise always point-like in any telescope, or at least was at that time. Nowadays, we can resolve with regular telescopes some astronomical objects, but usually some type of interferometry is what you need to use. And this is all based on this HBT discovery. And at the same time, independently, Goldhaber and collaborators found this idea applicable in high energy physics as well. A long series of papers and discussions was needed, and decades were needed to understand it. But now we come to the conclusion, or the general consensus of the field is that we can measure momentum correlations of momentum differences in high energy physics, and then they turn out to be related to the Fourier transform of the source distribution, which is the probability density of creating a particle at a given location. Or even better, we can express it with the distance distribution, so not a single particle source, but a distance distribution of pairs, and then there is no absolute value squared anymore, so the phase information better handled in this type of write-up. So again, the momentum correlation reveals the distance distribution, which otherwise cannot be resolved with any type of detectors. And then this gives us a technique to explore the geometry of particle creation in high energy collisions. The basic idea when this field started was that, of course, the geometry, because of random walks, will be Gaussian. But early on, even 20 years ago, it became clear that these shapes are not Gaussian anymore via a method called imaging. Source shapes were measured with this based on femtoscopy, and it turned out that these source images have power law tails. And the power law tails then brought on the idea that maybe some kind of anomalous diffusion or whatever else is happening, but we need to go beyond the Gaussian approximation. And then the first step in that direction is to utilize Lévy stable distributions. These can be defined, for example, in a spherical symmetric case in 3 dimensions like this. And then the most important part is that it contains an alpha exponent, and then the source will have a power law tail described by this -1 minus alpha exponent if alpha is smaller than 2. These distributions are meaningful mathematically for alpha greater than 2 as well, but are not positive. And we expect our particle creation probability density to be positive. So the playing ground for this alpha parameter is between 0 and 2. And then for 2, we get the Gaussian distribution. Alpha equals 1 is also special in the sense that this is the only other one which is expressible with simple analytic functions, and that is the Cauchy distribution. And then this can be utilized to understand source geometry. If we have a source characterized by this distribution, then the correlation function that is accessible in experiments can be written like this: 1 plus some correlation strength parameter and an exponential of momentum difference Q times momentum, source size R to the alpha power. So this is the correlation function. This is, so to say, in momentum space, and then in coordinate space, we have the Lévy distribution. Throughout the talk, sorry, yep. Yeah, right. Yes, so first of all, whenever I say source, I mean either the single particle location distribution or the distance, but your question is very adequate, is at the freeze out, or even more precisely at the point of last scattering. From then on, particles follow a straight path up to our detectors. I will touch upon the fact that this is a little bit tricky, because if we consider Coulomb scattering, then that never ceases to happen. So it's a little bit interesting what's going on, but what I indeed mean is distance distributions at the whatever type of freeze out. And then this is accessible via correlation functions. So in measurement, we do this, and then the R parameter describes the width, the alpha describes the shape, and the lambda describes the strength. And then this can be translated here, that again, R describes the width, lambda the overall integral, so to say, and then alpha the shape. Good. This has been applied, and such sources have been seen at various experiments from NA61 to Phoenix, STAR also, and the CMS as well. Yes? Yeah. Now I mentioned this is spherically symmetric. You can generalize this, and I will touch upon that when you move on to more radii. In fact, you can have even 6 radii if you consider cross terms, but I will come to that a little bit. The biggest problem is that measurements of femtoscopy always ended up by having a radius, 1 or 3 or whatever, but that was always a Gaussian radius. And it's not clear what a Gaussian radius means if the source is not Gaussian. As you all can imagine, if alpha equals 2, there is no tail, but if alpha is smaller than 2, then we have a power law tail. And then an RMS will become infinity, right, of the source. So what does that mean? That we extract the Gaussian radius of a source that has a power law tail. In practice, probably it would depend on the cutoff then that you apply your measurement or your calculation or simulation, whatever applies. Probably, nothing goes out to infinity. Detectors are at some distance. There is no particle creation at, a kilometer away. So anyway, it becomes a little bit tricky, and to understand it better, let me just show a couple of examples. This plot shows a couple of such spatial distributions. I'm not sure how readable it is, but the black curve is a Lévy distribution with 7 Fermi radius and alpha 1.3. And then the red and the green show Gaussian distributions with the same half width at half maximum and the same half width at half integral. So you can relate or connect these distributions by some, let's say, assumption-free source measures, the width at half maximum or the width at half integral, and then a Lévy distribution will correspond to some kind of a Gaussian distribution, and this may help understand what's happening. And you can also do some direct translation. You can calculate the Lévy versus Gaussian radius if you want to have the same half width at half integral, or half maximum, or half width at half integral. And for example, in that sense, alpha equals 1.3 and the Lévy radius of 7 Fermi means 3.61 Fermi Gaussian radius, or a 5.77 Fermi Gaussian radius. But whatever you do, you have to keep in mind that if you have a power law tail, then a Gaussian radius means something else, or is not even clear what it means. Okay, now what are the possible origins of this? I will show some origins and focus on one of these, but also will ask basically for your input or whatever ideas you have on the origin of this or the connection to the medium that we are exploring. So one idea that came up that can cause Lévy distributions is jet fragmentation, and basically the anomalous diffusion of anomalous dimension of QCD, how jets fragment, and that fragmentation that has basically a fractal nature, and that causes a power law tail. This is reasonable, for example, in E plus E minus collisions, where particle pairs are produced mostly by jets. In a high multiplicity environment that is a PP collision, or especially an ion-ion collision, there this is not so relevant. Another idea was the critical phenomena, because a medium at its critical point necessarily has no characteristic scale. Fluctuations appear at all scales, and this creates a power law. So no exponential, but a power law right at the critical point. This might be relevant in some of the regions. Of course, no one knows where the critical point is, if any experiments touch upon that, but there has been an idea that the Lévy exponent drops near the critical point to some critical value. It has even been suggested that the alpha parameter equals or is directly related to the eta critical exponent of spatial correlations. It has also been suggested that maybe this is all just because of averaging. We do directional averaging if we do one-dimensional or spherically symmetric assumption, or event averaging because we have in a in a measurement we collect together data from source sizes or collision sizes of this size, that size, and all of those Gaussians maybe lead to a power law tail. It turned out that this is not true because we've been doing event-by-event analysis of these shapes and 3D analysis, so this cannot happen. And that leaves us with only one plausible understanding or explanation for these power law tails, and that of Lévy-walk. Maybe there are others, but I cannot tell any, or I don't have any more ideas at the moment. But it's very important, even if we don't understand why it's happening, to explore the source or the geometry of particle creation, because if we utilize not the correct assumption, then our extracted parameters will not describe the source, really. Yes? Sorry? They, I'm not sure what you mean. So they always assume a Gaussian. Yeah. Yes, but yes, I have to say that I'm really struggling with this, that everyone says, oh, let's just assume a Gaussian. And why not? It works more or less. If you draw big enough data points, then it goes through. Yeah, but it's actually, I'm not sure if I show. Yeah, I will not show such experimental fits probably. So let me just go back where I am. But the problem is that in the case of correlation functions, the difference is not that strong, because there you have anyway the exponential. So in the correlation function language, the difference is smaller. And so visually is not that big of a difference in the source. You have a tail that is undeniable if you plot it. But here, the differences are actually smaller, and these parameters are actually very, very correlated. So it's visually not so clear. Of course, if you do statistics and say that chi-square, confidence level, whatever, then it's immediately clear that the Gaussian assumption is bad. But still, people don't want to work with that too much. No, what? So the simulations that I've seen are like when you do EPOS. So you just run some full blown thing, and then whatever comes out, comes out. You cannot put, or you don't put it on top of whatever you have. But I will touch upon it a little bit. Yep. Oops. Yep. Oops, sorry. The Zoom is lagging, and then, okay. This one? Yeah, well, every value here is non-Gaussian except if alpha equals 2. So, is that, okay. Yeah, okay, yeah. Okay, so let's focus a little bit on this Lévy-walk idea. I mentioned Lévy-walk, but sometimes it's called Lévy-flight. The difference is that Lévy-flight happens when there is no finite speed, when the walk or the steps don't happen in actual space and actual time, but in some imaginary space. And Lévy-walk is when there is a finite speed, which limits your expansion. But it's not really important at this stage. What is interesting that this kind of behavior has also been seen in solid-state physics, and this is a 2D simulation of an electron gas, how it expands under the Coulomb interaction. And the blue points are the calculation, and then the red line is a power law fit to the tail, and then this is a Gaussian distribution. And it's immediately clear that just this Coulomb potential alone, because of its long range, creates this long tail. And probably in no simulation will you ever have the chance to incorporate this in heavy ion physics. Or I'm not sure, maybe you will have the chance, but having every particle creating a force on every other particle is just impossible numerically. And also because it's so long range, it never cuts off in space or time. But in any case, this happens, and we did some calculations with EPOS and URQMD, and here I just show a couple of pion histories. Let's say the last point is where the pion froze out, is the last interaction that happened. Interaction, I mean excluding the Coulomb, which doesn't cease to happen, so strong interaction including decays and coalescence and so on. Something happens at the beginning, obviously with some nucleon, and then lots of processes until the pion stops interacting and then goes out towards the detectors. This shows, or these images show that that there is really a long way from the collision, and whatever you think happens in the QGP gets really heavily distorted through all these interactions. And so this is a long talk, and because of that I put in lots of side notes. And one interesting side note on this Coulomb scattering, the Coulomb potential has an infinite range, and so affects the evolution basically forever. As I mentioned, in solid-state physics, this has been seen to cause power law tails. But it's interesting that it's deeply connected, or it may be deeply connected to our correlations. Two-particle correlation signal can be illustrated by this diagram that a particle is created here, another one is created here, and then they are detected at these two locations. And then the two-point correlator is basically nothing else but the phase integral along this closed path. And the Aharonov-Bohm effect is that whenever there is some random field happening here within these closed loops, that modifies the phase shift, or it adds an extra phase shift, and this distorts the correlation signal that we are measuring. And this is actually also happening just because of the Coulomb potential that creates a random field within this closed loop. This can be illustrated by this exaggerated plot that the pion, after its last point of scattering, flies out towards the detector, but it's continuously a little bit wiggled by the electromagnetic interaction. And here, actually, this we calculated or made some toy simulation, how a particle transfers to its path is wiggled around by the field. And it turns out that this really decreases our correlation strength. And if we call lambda 2 the two-particle correlation strength and lambda 3 the three-particle correlation strength, if everything happens without this effect and fully chaotic source and so on, then this is 5 and this is 1. But if we have the same number of particles in a smaller and smaller volume, by particles I mean hadrons, then this correlation strength decreases. So this Coulomb effect may actually be very important, but this has not been explored in too much detail in the past. So this was only a side note to our main topic. Let me go back to this Lévy-walk and show you what's happening in, for example, in URQMD. In URQMD, the processes can be categorized in 4 types: scattering, which is a 2x2 process; a decay, which is 1 to n process; coalescence, which is a 2 to 1 process; and then string fragmentation, which is also a 1 to n process, but n being very, very large. And then all of these processes can be characterized by a step length distribution, where the step means the distance covered by the particle before the given process occurs. It's connected to the mean free path and the cross-section of that process, or the probability of that process. These are shown then here: decay, coalescence, string fragmentation, and 2x2 scattering, and then the total by red. This is a log-log plot, so it's quite clear that up to some cutoff, or truncation, it follows a power law tail, which is shown in this inset. There are some criteria in this field of exploring Lévy-walks, how to check these power law tails, because of course you never go to infinity. So So you always have to have some truncation, and then it's not clear when something is a truncated power law, or it can be described by a sum of 10 exponentials, for example. And then if you apply these criteria, it turns out that this is really a power law. And then from the step length distribution, you can go to the distance distribution. The distance distribution is really the probability distribution of the sum of many, many such variables. And as the general central limit theorem tells, if there is no finite second moment to this distribution up to a truncation, then our limiting distribution for the sum will be a Lévy distribution, again up to a truncation. And so the distance distribution already in URQMD without anything else is this Lévy distribution. Now, URQMD doesn't describe our processes very well, as it's known. So let's go to something more realistic. Let's go to EPOS, which contains, after some initial stage, also a hydro type of evolution. And the interesting thing is that in this case, we can check the source images at various stages. You can stop evolution after the hydro phase, and it appears that after the hydro phase, there is no power law tail indeed. It is describable by a Gaussian, but it's not really clear, because these are single event distributions. If this is just because there is a cutoff, after the hydro phase, there are not enough particles to have enough statistics at large distances. After the hydro phase, there are no bigger distances than, let's say, 10 or 20 Fermi, so we cannot see farther away. So it's not really sure, but it looks like, at least up to what we have, that it's Gaussian. Once you turn on decays, then some tail appears, but these decays are characterized by a couple of resonances, a couple of long-lived resonances, so these are not really nicely looking. If we turn on rescattering, so for example URQMD, then we really start to have very nice Lévy shapes. The red line on all of these plots is a fit, and then it turns out that in these 4 stages, so just the hydro, then decays, then also scattering, but without decays, and then everything turned on. Rescattering and decays is the last stage. The source radius increases, and the shape also changes, goes from Gaussian to having a strong power law. So this suggests that it's really the scattering phase that is needed for the Lévy shapes to appear. Just a cross-check, Gabriel, you mentioned 3D. In EPOS or URQMD, you can do the 3D in the outside long coordinates, which is the special pair coordinate system used in this correlation analysis. And this is, again, one EPOS event, a single event, and then in all the directions, a Lévy distribution appears, or better to say, it's describable by a 3D Lévy, having 3 radii, but 1 alpha parameter. So it works in 3D as well. Good, so these were so far the ideas that we had. And now let's move on to what I say are facts, but I mean really measurements. Let's start from a 200 GeV gold measurement of Phoenix. And in the individual plots, we see the alpha parameter as a function of momentum or transverse mass of the pairs in different centrality classes, 0 to 10, 10 to 20, and so on. Various centralities, we see that there is not so much of an empty dependence. These are mostly constant. And if you fit a constant to each of these, you get this plot, how the average alpha parameter changes with centrality with the number of participants. So these are central collisions and these are peripheral collisions. And it seems like in the data, the alpha parameter decreases for central collisions. It's a little bit counterintuitive if you think that Anomalous diffusion happens because the mean free path is getting bigger and bigger, and always you do a step, and then the mean free path increases even more because the system gets more and more diluted. So if you start from a denser system, you could think that maybe then alpha will be closer, or if it's denser, yes, then it will be closer to a Gaussian, but it's the opposite. The denser the system, the farther away from Gaussian it is, maybe because of the longer evolution time. We don't know at the moment, but this is what we see. I will show some comparisons. Now, we can explore also the momentum or empty dependence of the radii. This is some characteristic trend that is always seen since the dawn of femtoscopy, and it has been basically predicted by hydrodynamics or by flow, that because of the explosion, particles that have a bigger moment, they come from a more confined space. This is like Hubble flow. You look at your source from one direction because you look at momentum correlations. Momentum correlations means small momentum differences. So you look at pairs that go in the same direction. And particles that have a large velocity or large momentum, they come from the outer regions of the fireball because of the Hubble flow. Particles that have a smaller momentum, they come from a bigger region. And then all of this is affected by the temperature. The temperature puts some random variance or scattering on that small volume. So it's the temperature and the velocity that explains this behavior. So far, the conventional wisdom from traditional hydrodynamics, but we saw that the radii that are there, or the source that is characterized by the freeze-out distribution, is very, very far from the Gaussian one or from the hydro phase. So all of those scatterings drive us away from the hydro freeze-out, the quark hadron freeze-out. And so it's entirely not clear why this is true still, or why this type of hydro prediction still holds in case of a Lévy source or a Lévy radii. Actually, I show some comparison here. This is the same measurement from EPOS with the decays and the scattering and everything turned on. And we see that it's there as well. So it must be not a big mystery because it's there already in EPOS, but it's a little bit black box type of thing. So it's still not clear. But let me show some more comparisons. If we look at the radii, this is now 3 dimensions, outside and long. There is quite good match with an EPOS type of simulation, but we see that there is a big discrepancy in the shape. This plot shows alpha versus momentum in experiment and in EPOS. This shows alpha versus number of participants, so centrality in measurement and in EPOS. We see that in EPOS, indeed, as the system gets denser, it gets closer and closer to Gaussian. But in experiment, it's entirely the opposite. For the biggest system, the densest system, we are the farthest away from the Gaussian distribution. And it's at this stage entirely not clear what's the reason for this big difference. This is the 0 to 10% centrality, where the difference is the biggest, as a function of MT, and then these are the MT averaged values. So this difference corresponds to this difference. It gets then closer once we go to peripheral collisions. So something is not there in EPOS, even though it's really full simulation containing lots of stuff. What it doesn't contain is, of course, this Coulomb scattering. If that is the culprit, then I'm not sure if we will ever have the chance of really calculating it with some analytic models or some more theory-inspired models, not so full of everything like EPOS. Good. Now, let me show something else, why this is important. This is not connected too much to hydrodynamics, but it's quite interesting, so let me show it. One more parameter of those correlations that I mentioned is the lambda parameter, which describes the correlation strength. It is connected basically to the number of pions, if we look at pion-pion correlations, that are produced from the hydrodynamically evolving core, or so to say, that are directly produced, which are not produced after a long Lévy flight of steps because of decays and whatever. And then we could say that the square root of this lambda parameter is the core pions over all pions, the total number of pions. And we see that this lambda, it's a little bit masked by huge experimental uncertainties, but there is a characteristic behavior that it decreases for lower momenta in all centrality classes in this measurement. It's better visible if we divide out the large empty behavior. We take an average here at the large empty points and divide by them in the experiment. Then all of those uncertainties cancel. And here is the result, a lambda scaled by its maximum. These are the data points. And what's interesting is that this characteristic behavior can be explained by something that seems completely out of context, UA1 restoration. It turns out that, that the eta prime meson gets its mass from the explicit breaking of the UA1 symmetry, and if it's restored, then it would have a smaller mass. If the eta prime would be created with a smaller mass, then its production cross-section would be enhanced, and there would be a larger eta prime content in our sample. And that would mean there are more same charge pion pairs. It turns out that kinematically they tend to be at low transverse masses, and the same sign pairs appears because of this decay chain. Eta prime goes to eta and 2 pions, and then the eta also goes to pions, and then you will have same charge pion pairs from this decay chain. And it turns out that you can plug this into many thermal Monte Carlo models, let's say resonance cocktails, enhance the eta prime content from the beginning, and then see what comes out. And it turns out that the data are compatible with a mass drop scenario and incompatible with a scenario that doesn't incorporate a mass drop of the eta prime. This is within this framework. It's very, 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 very indirect. So additional measurements would be needed to confirm this. Nevertheless, this is a measurement from Phoenix based on this that we did of the modified eta prime mass as a function of collision centrality. And we see that the eta prime mass is always in each centrality class, except the most peripheral one, away from the vacuum mass or the PDG mass, so to say, and it becomes closer to the eta mass. Yes? Yes, exactly. It's from this. No. No, not at the required momentum. You can measure eta prime. So first of all, this decay chain has a very low branching ratio. But you... Yeah, so if you would go after this, then you would need at least 5 particle, but in fact 6 particle correlations, because this is then 2 photons also, the pi zero. So this is... And then there would be just such a big background of combinatorial, so it's impossible. But you can do it via the 2-photon decay channel. So the eta prime also decays, and that's the most important decay to 2 photons. And with that you could do it, but the unfortunate fact is that that only is possible with very high momentum photons. Yeah.
Essential mass shift has been observed in hadronic decay channel so far, right? So the question is now why would the eta prime undergo such a huge mass shift in hadronic channel, whereas we don't see this for
Okay. Yeah. So there have been lots of effective theory calculations, and I can only advertise our Zimányi school, where lots of such results are always presented, and it's plausible that the eta prime undergoes this huge mass shift from those calculations. But the important thing to keep in mind that, of course, everything goes back on mass shell or to the vacuum mass when it's detected. So it's not so trivial how to access this mass modification. But from the effective theory calculations, it's not unreasonable that, for example, the eta prime would go to have a mass close to the eta.
when you observe, for instance, the resonances with an electronic channel, you may say like this occurs before the freeze out. Sorry. You may have decays occurring in the plasma phase, and therefore you see some mass shift.
Yeah, so for the rho, traditionally the rho was where it was ruled out basically, but it's possible that the rho does. So all of those calculations show how the masses change with the temperature, and it's not trivial, and this is a possible scenario. But let me just tell that from the experimental side, what happens is that without the modification, you have such an eta or eta prime spectrum, and then with the modification, you would get something like this. There would be an additional increase here, but you can measure, let's say, only in this part. And then it's really an exponential thing, and then you see a very, very small difference. So it's experimentally not accessible at this stage for this particle. So, but we don't know. This is very indirect, but also very interesting. Yeah, so no, the pion spectrum, it's from the eta primes, only a small fraction goes out to same charge pion pairs. If you go from the other direction, you can look at the pions, then I think a couple percent, if I look at one of these thermal models, then it says that let's say, I remember the pairs that to the pairs the eta prime contributes, let's say, 10%. Yes, but it's smeared. But it's smeared in the single particle spectra. This appears in the pair spectrum or the correlations, basically, because there it's characteristically happening at the low empty region. Because the eta prime has this, let's say, this decreased mass of a couple hundred, let's say 600 MeV, and then we need to produce 5 pions. So it needs to go back on shell or to the vacuum mass before it can decay, but still there is not much momentum available or not much energy available for the pairs. So in the pair spectrum, it's visible, but the eta prime itself can have a large momentum, and then the pion spectra are not so clearly affected. It's the number of pions that is somewhat affected, but it's not that well reconstructible. But there haven't been so many calculations. So, any? Mm-hmm. Mm-hmm. Actually, yeah, so if, anyhow. But, if anyone has the time to plug in, more pions from an eta prime, and maybe, that does something, but it's not so easy. Yeah. is extremely strong, but it has been. Yep. But E plus E minus collisions, you mean like lap? Yeah. Yeah. But it's driven by not by the medium, and especially not by decays, but jets.
Yeah, but it's you know, scenarios we think of less of hybridization than hybridization, and then followed by atomic or heavily scattering and running case. Essentially, so the difference is that we think of the hybridization, and then in heavy ions we think that these are the scattering state. In plus and minus, they do not have enough fun.
Yeah.
Yes, it was in minus. This was the prime is measured in this channel. One of those channels.
No, it may be some E plus E minus channel or a diphoton channel, surely not this channel. Okay, okay, yeah, then I don't know. It may be possible because of the small combinatorial background. Yeah, okay. Of course, there you don't expect any symmetry restoration because there is no hot medium there.
Yeah, right. But the fact that I mean, I would expect something like a small mass shift because I mean this is a very channel. In the end, you have a 30%, 40% difference. I don't know. So what was the comment to be? So how was this result? Say, I didn't know. Sorry. How was this result? Say, received?
Well, so it's a PRC editor's choice. So the PRC editors liked it a lot. But yeah, okay, so if you allow a personal comment, I have been working on this since 2003. So more than 20 years during my master's thesis already. I started to work on it, and then Bill Zeitz was the spokesperson of Phoenix, and then he said that we can comment on it like this being not incompatible. And then from this non-incompatible statement and not being allowed to show such plots of direct comparison with different masses, we went to being able to show this because it's experimentally very solid. And then I think if you put the explanation that, well, okay, this is indirect, and I don't think that we can claim the measurement or discovery or whatever, then it's fine. And then we just invite everyone to do calculations which can explain this without a mass drop, or experimental groups to do new measurements in the diphoton channel or whichever channel. Yeah. LHC hasn't measured this yet. Usually, the lambda parameter, it's actually even a niche thing in femtoscopy to measure lambda. Lambda is usually treated as a nuisance parameter. That, okay, so there is some strength, okay, but let's get rid of it. Because it depends on lots of stuff, and especially, this can, in LHC, only Alice can do it. Because you need very good PID for that, but Alice doesn't do anything but Gaussian. And if you do Gaussian, then your correlation strengths will not be real. So that's why they don't like it, I think. But I'm not sure if anyone has any Alice connections here, but yeah. Okay, yeah. Good. Yeah, I think I need to speed up a little bit. So I'm exactly at the half of the talk, but lots of stuff I can just skip. This has been measured also at STAR. It's very, very different experimentally. Nevertheless, the same thing comes out, the discrepancy with EPOS. So experiment shows decreasing alpha, EPOS shows increasing alpha, the same radii versus empty as predicted by hydro, and also the same lambda versus empty behavior has been seen at star. These were all been one-dimensional measurements. We can move to three-dimensional stable, or well, three-dimensional but spherically, sorry. So this was all that I showed, star or phoenix, spherically symmetric assumption. We can go to anisotropic Lévy stable distributions, where then the radius becomes a matrix, an R-squared matrix, and then, well, this is the distribution. You can redo the analysis, and then everything is compatible. The source is spherically symmetric enough in the longitudinally co-moving frame, by the way, so that the spherically symmetric assumption works, and the 1D and the 3D analysis is compatible. Here is a 3D alpha. This is important because it has been suggested in the past that we see the non-Gaussian behavior only because of directional averaging. But it's not true. Even in 3D, we see alpha very far from 2 and actually compatible with the 1D. Lambda measurement is even harder in 3D, but this type of behavior is somewhat recovered, although this is a preliminary analysis. Here is a comparison to EPOS. The radii match quite well, except in the side direction. There is some discrepancy here, and then the same discrepancy between the EPOS and then the measurement is seen. EPOS thinks or sees results closer to Gaussian. Now you can do analysis at various other energies. Let me just flash through these. This is going down from 200 GeV to 7.7 GeV. Radii behave the same. Alpha, so the random walk or Lévy exponent, this is 200 GeV, 45, and so on down to 7.7. And we see a little bit of an increase. I will summarize this on a plot later. Let me also show the lambda measurement. This is that decrease at low empty, and then there is some of this behavior seen still at the lowest energies, although not that strong. Yep. Yes, so I have a backup slide on that. No, but I will, no, wait. I'm not sure how I can go there. I cannot go there. I have to manually page down. Anyway, yeah. So what? It's not just on that, but so the basic idea was that if you go to this three-dimensional thing, and then the out minus side direction will be a proxy to emission duration, and then at the first order phase transition there will be a huge transition duration, and then if you measure this R out minus R side squared, then it will show at least a peak or a step or whatever. And then star data are shown on this plot, this R out squared minus R side squared versus collision energy, and then there is a peak. And then people even use that to extract the critical point information and locate the critical point. But all of those measurements happened with Gaussian assumption. The issue is, and I was just coming there, that the shape changes with energy. And your Gaussian radii entangle the size information and the shape information. And if both change, then you are not sure what you are doing or what's really happening. And then here is a mock idea that we did. What happens if all those measurements would have been done with the Lévy assumption? We can have some scaling. There is a scaling variable that seems to be independent of the alpha assumption. And then you can use that to scale your radii from the Gaussian assumption to what would happen if alpha would be something else. And then it turns out that this difference would have a very, very different shape. There would be no maximum, but there would be a somewhat constant line and then a decrease. So even from the experimental side, it's not so clear what's happening if you do the correct assumption. Much less so from the theory side or phenomenology side, because this entire emission duration business is a little bit interesting, or there are lots of ingredients to it. Okay. Let me go back to where I was and speed up a little bit. So we did also fixed target energy measurements at star. This is alpha versus MT again at fixed target energies. Alpha is still far from 2. And then let me just jump to this plot, which summarizes all the alpha measurements as a function of collision energy. Okay, so alpha decreases or seems to decrease with collision energy, getting smaller and smaller, so farther away from the Gaussian baseline or line at 2 for the densest and highest multiplicity system. So this is similar as what we saw with centrality. This is illustrated by having 2 points here. This 1 point, the upper one is for more peripheral, and then for more central it goes down, and with energy it really goes down smoothly. So the denser the system, or the bigger the multiplicity, the farther away we are from Gaussian. Maybe this is because of longer time available for rescattering. It's entirely not clear, and it becomes even less clear if we put EPOS on top of it. EPOS goes the other way. EPOS says that the bigger the energy, the closer we are to Gaussian. So entirely the opposite of the data. So I have to say that this is absolutely not clear. The only idea I have is that the long-range Coulomb interaction is, of course, missing from the EPOS. But I think, and that's why this talk is maybe useful here, that even the hydro part may have challenges. And it's not just the hydro that is put into EPOS that is at play. Same thing measured at Na61, argon-scandium collisions, beryllium-beryllium collisions, and compared to URQMD. Now, interestingly enough, URQMD suggests a decrease in alpha, although a very, very small decrease with collision energy. But Na61 suggests more a constant or even a minimum-like behavior, although the uncertainties here are very, very large. And there are measurements upcoming in a bigger system. So this is argon-scandium, which is around 40 in atomic number. Xenon-lanthan will be much bigger system, much better, much bigger number of pairs. And so let me put everything together. The Na61 and the rig data points. This is argon-scandium, this is beryllium-beryllium. These are the rig data points from Star and Phoenix. And let me put the CMS point also on top, which is completely away. Even more mystery. I have to say the CMS is a little bit different because there is no PID in CMS. But we have been doing studies, and it seems like that PID doesn't affect this. So we can do the measurement assuming all particles are pions, and it gives the same result. Yes? No. Hades didn't measure this so far. Hades also sticks to the Gaussian assumption so far, but maybe not for too long. Yeah. So this is the experimental landscape so far of this alpha. If we bring back the critical point idea, then what we would have loved to see is that alpha here decreases by a lot. There is no such decrease. There is a small decrease here, although maybe there is no critical point available to experiments. Maybe it's down here, so we don't know. But anyway, there is a smooth behavior. except this little trend by Na61 and except the CMS data point. So it's not clear what's happening, and now let me finish, but I still have a couple of slides, so it's a slow finish by lots of questions. What's going on? So what are the experimental observations? The experimental observation is that we see Lévy stable source shapes very far from the Gaussian, and we see the radii follow the hydro prediction. And then the simulations say that hadronic scattering and decay altogether can be called the Lévy-walk, create this Lévy stable source, and this very, very strongly modify the source size and the source shape. But still, the radii follow the hydro prediction, and the predictions or the results on Lévy exponent significantly differ from the experiment. So it's not clear how to reconcile this, and I just would like to advertise this problem and ask for ideas or calculations, what could be done. From the experimental side, there is still one thing to be done, and I will show it, the particle type dependence. Because if this all happens because of hadronic scattering and decays, then kaons will behave very differently than pions. Kaons undergo different decays, they have different cross-sections on every type of scattering, so we should see something. From the phenomenology side, I think one important question is if the hydro phase can contribute to these power law tails through some anomalous hydrodynamics or whatever. Let me first discuss this with the particle type. So, as I said, the power law tails in simulation seem to be due to this Lévy-walk, this scattering process of all kinds of processes happening. So there has been this idea on the market, so to say, since a long time, that based on just elastic scattering, if there would be not all of these processes, just elastic scattering, then the proton alpha would be the biggest, pion alpha would be smaller, and kaon alpha would be the smallest, because the mean free path is the largest for kaons. They have the smallest cross sections, and protons have the largest mean free path and smallest cross section, and they have the largest cross section and smallest mean free path, so the largest alpha. This is recovered in, for example, the hadronic resonance cascade or humanic resonance model. The tails of pions are between the kaon tail and the proton tail, but this is only elastic scattering. Let me move on and show what happens if we do EPOS and measurement. EPOS says that the kaon alpha is comparable to the pion alpha and definitely not smaller, contrary to the elastic scattering idea. And in experiment, we see within huge uncertainties the same alpha for pions as for kaons. Maybe a little bit bigger, but definitely does not seem to be smaller. Even more interestingly, we see a perfect scaling of the empty dependence of the radii, both in experiment and in EPOS simulation, for pions and kaons, as if rescattering wouldn't have distorted the shape, because this is what hydro suggests. Hydro says that particle type doesn't matter, just empty is what matters, and everything will scale with transverse mass. All particles will fall on the same curve. But it's very, very not clear why does this still hold after all those processes, after all those decays and scatterings and whatever that's happening that is very different for pions and kaons. So I'm sort of out of ideas, but let me tell a couple of things. What could be done? For example, let's take some very traditional hydrodynamics like it was done 20 years ago. Let's take a Maxwell-Hüttner distribution with some type of Cooper-Frye freeze-out with some density and flow and temperature and so on. And then somehow the conventional wisdom is that hydro cannot produce anything but Gaussians. There is no way hydro produces power law tails, but I'm not sure if it's true. And to test this, let's see. Let's try to come up with something. For example, you can have a simple Hubble flow solution. And this solves the relativistic hydro equations without viscosity. I know that this is not so realistic and everything, but you can have some solution which creates a Lévy-shaped freeze-out distribution with Cooper-Frye and this term and everything. It's unfortunately not really realistic. If you create something like that, this would result in completely crazy observables. So the tough part is to create hydrodynamics that creates reasonable observables. Let me show another example, which is a non-solution. So its time dependence doesn't solve the hydro equations, but it still can be treated as a freeze-out distribution. Flow field, density field, and temperature field at freeze-out, and then the capital L denotes a Lévy distribution. If this happens at freeze-out, then this type of Cooper-Frye results in roughly reasonable observables, and numerically it can be evolved back in time, but we are not sure, of course, if this would result in a reasonable initial state. But I think the more realistic way to go is to understand that it's not the normal diffusion and the normal walk that is inside hydrodynamics, the microscopic part of hydrodynamics, but maybe the superdiffusion and, of course, subdiffusion that can create such a thing. For example, well, okay, so you can define these fractional derivatives with many different frameworks. For example, this Caputo version of a fractional derivative is used mostly, and then if you define or start from a fractional diffusion equation, that is a fractional derivative in time and a fractional derivative in space, then you end up with subdiffusion for large alpha and superdiffusion for small alpha. And if you take still regular derivatives in the time direction, so gamma equals 1, then for alpha equals alpha between 0 and 2, you end up with Lévy stable distributions. So my point is that what if superdiffusion happens between the hydro part, where the mean free path is small and diffusion is normal, and the free streaming, where mean free path is infinity, basically? What if between the two parts, but still describable by some kind of an maybe anomalous transport, this thing happens, and it's not just the rescattering and the hadronic phase that creates the power law tails. That would explain the particle time dependence at least. So I think I'll end here, and let me just mention that the main goal with all of this is to somehow connect the power law exponent alpha to something physical. Because it's okay that we can extract it, but what does it mean? What kind of connection does it have to QGP or QCD or whatever? In a jet-dominated environment, like in E plus C minus, it has been shown that it's connected to the anomalous dimension of QCD, or may be connected to it. At the critical point, it may be connected to the critical exponent eta, but in all data that I have shown, none of this seemed to matter. So it's something else. Maybe it's the hadronic phase, maybe it's the QGP phase, and I hope that soon we can get a better understanding of all that. And I just leave the summary slide up, and thank you for your attention. Oh, and let me not forget to advertise our conference in Budapest. It's not so much of a question what I would like to, but yeah. Yeah, so unfortunately, I scanned the literature, and as far as I understood, is always being said that, okay, so we simulate microscopically, and then we say that it looks like a fractional derivative. But I didn't understand if a connection is being made.
Our series of k, and the leading term is k squared.
Mm-hmm.
To have something assume that omega is a function of k, because you have fractional power, so you cannot.
Yeah, then no series basically. Yeah.
Coefficient is formally divergent, and dispersion relation is non-analytical. I don't know. Do you have anything?
No, but the basic idea I have, but this is just this, I can just draw a line that, so let's imagine that the mean free path is increasing like this, and then you make steps, and then you make a step, and then the next time you sample the system, the mean free path increased, and then it increases even more, and then if this becomes of, let's say, some kind of a fractal nature, then you end up with this kind of fractional derivative type of equation. And maybe it's the time dependence of the density that drives this, or the time dependence of the temperature, if there is a temperature, and then this, but I really have no handle on this mathematically, what is happening there. Probably yes, but yeah, so it's something similar. The important part would be there to connect to physical properties, because you can describe it by some equation, but yeah, it would be nice to understand, and especially because there is this density or multiplicity or whatever dependence that is the opposite in epos and in data. So that would be good to understand why in bigger systems alpha is smaller. I can say that, oh, it's because of the longer time available to do diffusion. But if it's just that, then it's surely in epos as well, and epos doesn't say that. So that's kind of the question.
So I have a question. So with Derek and Alexander, we study critical kind of phase transition.
Mm-hmm.
When the question kind of phase transition, and we found that you produce a lot of fun. The soft bind is their momentum is really so the level of their mass, and they should be correlated as a critical correlation.
Mm-hmm. But what kind of phase transition you mean? Okay. Yeah, so yeah, so then the question is if but it's not on this landscape then, because it's but it's sure that if you have a second order phase transition, then correlations will appear at all scales, and then you will have a correlation exponent and then a power law 2-point correlation function. But in experiment or in reality, that may happen at the QCD second order phase transition point, if that's accessible by experiment. Any other second order phase transition, I'm not sure if or how it's observable. Okay. Thank you.